Yep, so thank you, Mel. Now I will just continue from what Mel actually said and also what Dirk already presented about our work and about models and, let's say, conceptual models. So in the past, in the last 20 years, we've known that there are multiple studies who showed either with calculations, with models, or just with a concept that enhanced rock weathering has a huge chance. Now you can see with the years that it's getting less per year, but let's say we recognize that at least the stoichiometric potential is pretty high. And from the stoichiometric potential, we now want to go into what is actually the potential with our data. Now, you already have seen in Dirk's presentation the greenhouse, and the setup, for the ones who don't know about that, just looks like this. So we have a collection tank where we store, or let's say collect, our leachate water of our experiment. In the upper part we have our soil, and in the upper part of that soil is mixed with our feedstock. Now, why greenhouse? You already heard from Dirk, we want to go into a more controlled area to see actually weathering and the signals and understand them. Now, there are even more reasons why. So, of course, the accelerated weathering with a controlled temperature above 19 degrees Celsius and an irrigation rate from 2,000 millimeters per year up to 4,000 in extreme hot summers in a greenhouse. And you have a high throughput of different soils in one location where you can actually measure them all together. Now, another advantage is we are running these experiments for more than a few weeks, which is sometimes related to project times, etc. So the results you will see today from all the different scientific teams are actually covering 2 years of an experiment. And yeah, so in the field we just used a bentonite, and in the greenhouse we wanted to see how different materials, which are maybe reacting faster, are actually showing a faster signal on different soils. Therefore, you will see online in a PDF in a handout called cheat sheet, and here in the room on the paper you have on your seat a description for our sampling code and for our greenhouse, which will be discussed today. So on the left you just have in this table a list of our soils. So third one is actually the third soil from the outside experiment, and LUFA 2.1, 2.2a and 6SA are actually standardized soils from the LUFA Institute in Germany. Now you will have something on that sheet which looks like this, which is describing the sample code and what the sample consists of. So the first digit is actually the table where we had our experiment on, describing the soil, so one of the 4 here. There's one exception, which will be Xavier Duplat with FIRD 2, which is another third batch, but we're coming to that later. And you have another figure like this on the cheat sheet, where it's describing the soil texture and at the bottom, the feedstocks. So the second digit in your sample code is the feedstock, and the fourth is actually pot layer because we cut it into halves, but we will come to that later. With the QR code, you can actually find and access even more data about the feedstocks and about the soil. Now, yeah?
What is the unit of the cation exchange capacity?
Yeah, so that's listed in the QR code in the table. So it's CEC effective, and it's C mole per kilogram. So, like Dirk said, we haven't found anything in the field. Now, as you can see here on the right, there are the accumulated alkalinities of the greenhouse over time. And it doesn't look like that the blue line, which is the control, is actually beaten by the treatments. Actually, the treatments are lower. So we could prove with our greenhouse experiment that we're seeing no increase in alkalinity like outside, which in the first place looks a little bit like a sad picture of a greenhouse from AI. So you have no really found an increase in alkalinity in your greenhouse experiment, but that is actually not a bad thing because it looks like this in a greenhouse. So the failure actually showed us that it's way more complex than just spreading rock and getting a good signal. And it wasn't money, so down the drain from Dirk. It was actually a chance and door opening to understand the system better, because if this wouldn't have happened in the field, maybe there wouldn't have been a greenhouse. And without the greenhouse samples, there would be no symposium where we will discuss today really some more details about enhanced rock weathering. So coming back to the greenhouse, it will be really short now. The main takeaway from the leachate is actually that we can follow a certain trend with the different, let's say, dissolution kinetics of our materials. So from the very high alkaline steels, like on the far left on the x-axis, towards the more mafic on the right, you can see that the faster dissolving and reacting minerals are creating a higher median value in Ta, which is on the y-axis. Now, this is not everything, because you can see with the different colored dots that depending on the soil, the results really drastically different. Now, coming to the point of soil, because the soil makes, let's say, a more difference in the total amount of leachate alkalinity, what you can see here is the red diamond is the control value of accumulated alkalinity over 2 years in the upper part and on the lower part of 1 year. And the blue bar is the treated mean of leachate alkalinity, while this gray line is the range of all feedstocks added to that soil. Now, if you look at certain soils like Lufa 2.2a here, you can see that the control is slightly low in comparison to the feedstocks. While if we now look at way more soils where we applied mainly basalt, you can see that this red diamond is quite often at the same position as the feedstock or even higher than the feedstock. So something is going on in these pots, that must explain why there is less alkalinity or the same, even if we add rock. And here's just a short, let's say, glimpse of the preprint we published on BG, which is showing actually the different cation pools in our soil after 6 months and 12 months. So on the left, we have one soil called Lufa 2.2, and here we have our Lufa 6S, which is more pH like neutral to 7, while we have here an acidic soil with more sand. Here we have more clay. Now, on the left, always, you see the control after 6 months and the treatments, and here you have it after 12 months. You don't really see that after 12 months, the different pools, which are shown here in different colors, so exchangeable fraction, the carbonate fraction, the oxides, and the clays are increasing. Actually, pools are slightly decreasing, and the leached alkalinity is increasing. While in a pH neutral soil with clays, we somehow have a build-up in these pools. And that's one of the things we want to understand today and in the future, not only today, how these processes are actually working and how it's coming to this result. Now, there are 2 ways now to go further. One is deeper, so that we look at really details in science and academia, what is going on exactly with cation pools, what is going on with organics, and one is wider. Can we actually understand all of these, let's say, different behaviors with scaling up more experiments? So can we understand it better by building up more experiments with different soils and different feedstocks? There will be a presentation from me in the afternoon about the wider, so please stay online at the conference. And now we focus on the deeper to understand actually what is going on there. Now, as Dirk already mentioned, we are standing here today because in last year, September, we published a blog article where we were asking for proposals for different projects to share samples to understand these interactions better. And we sampled through the experiment biomass, dried it and stored it. And after our 2 years of leachate collection, we also killed our pots. And we killed them in 2 different ways. So the majority of the results we will see today are following the route 1, which, let's say, describes the sampling of the main pots. So the controls, the feedstocks, basanite with 40 tons per hectare, the diabase, which is a metaposal with carbonates, the ultramafic peridotite, and our steel slag. So we dumped the bucket, as you might have seen in the video which was running in a loop at the beginning. We cut it in half because originally we applied in the upper part the feedstock and the lower part just soil, which was, let's say, mixed due to bioturbation. And then we homogenized it wet, put it into a tray to dry it, and after that we mortared it, sieved it, and had a pretty homogene sample, how homogene you can call a soil sample. On the other hand, there were experiments where we did not focus too much on with leachate sampling because of the scale of our greenhouse experiment. Therefore, on these experiments with basanite dose variants, we just took 5 auger cores of the entire column, mixed them together, homogenized it wet, dried it also, mortared it, sieved it, and we had one mixed sample of the entire bucket. We sent it to our proposal center projects, and they will actually look in the following things today. So we will have a look into the plant, what the plant actually takes up, what does the, let's say, weathering process to the quality of the plant, and also what maybe what heavy metals can appear in the plant. We will look into secondary mineral formation and in cation pools. We will also have a look in the soil property and if we can maybe understand with just the exchangeable cations why this is so complicated in different soils. And we will try to understand what is going on with the organic carbon in the soil, because we have done some CO2 flux measurements where we've actually have seen an increase in CO2 efflux in the treated pots. So where's this carbon coming from? Are we stabilizing carbon, or is there even a good method to determine that? And with that, I'm nearly done because I'm again pointing at the cheat sheet. On the back of the cheat sheet here in the room and online on the second page, you will just find a roughly overview of all the presentations and projects of today with the method and the sample which was sampled. And with that, I thank you for your attention. Yeah, and our next speaker will be Mike Calland. So